So the question becomes, how far can we take stuff from 100 and 102? What can we do with just material balances, energy balances, and thermodynamics? How can we learn more about a reacting system? In a class like CENG 100, you would have learned just probably the basics of reacting systems. So in CENG 100, we kept having these systems that just looked like boxes, black boxes or white boxes. And about as far as we could go with each one of those was to put a temperature on there. You may have gotten a pressure, maybe not, and then some molar flow rates coming in and out. So N sub I is, actually it didn't need to be a molar flow rate, it could just be the number of moles in the reactor initially. The I means some species I, and the 0 just means before it went through the reactor or before the reaction started. Coming out the other side, we had some new temperature and some new number of moles. This would have been around either the very beginning of CENG 100 when we were just talking about material balances, or then towards the end when we started talking about the energy balance for a reacting system, we added a little bit more to this. The one term, actually we'll get to it in a minute, the material balance for this, we probably started with just the words in minus out plus generation minus consumption, which we probably would have noted that this is not a word equation that's restricted to a material balance. You can write one of those for an energy balance as well. The unique thing that we introduced for a reacting system for generation and consumption, anybody have me for 100? A couple of you? How do I pronounce this? Squiggle. It's the Greek letter xi, or which I think is actually pronounced ksi, which is not particularly natural to my speaking language. Some people call it xi, some people call it si, I call it squiggle. The squiggle, though, that we had was the extent of reaction. And we just defined this for no particular reason. As the moles leaving the system minus the moles entering the system divided by the stoichiometric coefficient for whichever species you happen to be talking about. And we just had that as a definition, and we kind of lumped all the generation and consumption into that single term squiggle. It happens to work pretty well. In order to use squiggle, we needed to know what that stoichiometric coefficient was. And so we had defined a general reaction like this. A plus B goes to C plus D. And so each one of those stoichiometric coefficients looked like A's and B's and C's. So reactants were negative and products were positive. We keep all of that same syntax for this particular class. We do the same thing. It's still new as a stoichiometric coefficient. That's still negative for reactants and positive for products. The one thing that we can change is in a real system, reactions usually aren't one way. So I drew that arrow going just to the right. Surely somewhere in your chemistry class you would have learned that most reactions are actually reversible. Which means you can take some of those products and turn them back into reactants under certain conditions. And so we want to know a little bit about what those conditions are. Does it sound like my mic just went off? Okay, recording has resumed from the battery. So a real reaction actually goes a little bit backwards. You take a little bit of product and you turn it into reactants. That's about as far as we took CENG 100. It probably didn't feel that way when you were doing CENG 100, but it was taking this information and applying it over and over and over and over again. Eventually we figured out how to do that with an energy balance, but in terms of energy balances, I'm going to leave that for 102. This is about everything that we did in 100. In 102, two of the big things that you would have learned were conservation of energy. So conservation of energy for a closed system, I'm going to write this in differential form, was that the internal energy was equal to the change in heat, or the heat added to the system, dq, plus any work that was added to or removed or done by the system. And you probably learned a bunch of conventions about when those are plus and minus. What's the Q, what's the W look like for gases and things like that. Don't worry, we don't have to go into any of that here. But this was the first law of thermodynamics, which again is a review from CENG 100, right? It's the same idea as what you would have gotten in CENG 100. It's just looking at it in a slightly different way. Most of the stuff in thermal probably would have started off in a differential form or gotten there eventually. The irritating one in CENG 102, or any thermodynamics course, was the entropy one. So the entropy change of the system plus the entropy change of the surroundings had to be greater than or equal to 0. And so this was our second law. That was something brand new in 102 that never came up in any form in CENG 100. The equality there, remember, holds if something is called reversible. So if it's an idealized system, then the entropy generation is 0. The big problem with entropy generation is to get into this mindset that we only need to calculate the entropy change of our system. Second law doesn't hold if you write an entropy balance of just a system. You have to count the rest of the universe. This is about the only time in chemical engineering where we relate our work to the universe. It's through the second law. You can't use the second law unless you know something about the universe, which is that ds of surroundings. So this one was everything else, right? That is not your system. And we have to keep that in mind. This one, the subscript T, is your system, or sorry, your superscript T is your system. Right, and so now our question is, if these are the basics, right, if we know we have a material balance from 100, we have an energy balance, you can pick from either 102 version or the 100 version, and we have an entropy balance from 102, what can we learn about a reacting system? We can actually learn a single incredibly important inequality. Almost everything ends up being an inequality because the second law is an inequality. And so in order to do that, we're going to start with not even an idealized system. This is, in addition to the stuff you would have done in 102, it's one of these times where we can finally not talk about an idealized system like we did in 100, where everything worked just the way that we wanted it to. What if something actually functions the way that it does if I had a reactor sitting in front of me and things were bubbling away? Which is nice. We don't get to do that all that often. So we can still take our reactors. We have gotten no better at reactor design than to build boxes, but that's okay. Everything outside of that reactor is a surrounding. So we can still get stuff to go into and out of our reactor, at least in terms of energy. So we can exchange energy with our surroundings by either some kind of a thermal gradient, which is our dq. Can everybody see the red okay, or is it a little pale? All right, I'll try to make it a little brighter next time, but you seem to be okay. So we can exchange energy with the system. For now, we're just going to assume that that system is closed so we don't have to worry about mass going back and forth. Everything inside the reactor, this is our actual system. So inside the reactor, we have molecules moving around. I'm going to draw it as a gas phase, but there is no reason to assume that this is gas phase. It will work just fine if you do a liquid phase. Molecules are moving around. They are presumably reacting. We don't know how that they are reacting at the moment, but we do know that they have some properties. The general properties that you should be able to recall from thermo, temperature, pressure, total internal energy, total entropy, that sort of stuff, and a total volume, V superscript T. So everything that's got a T on there is talking about the total internal energy, total entropy, total volume of the system itself, the stuff inside of our reactor. There's similar stuff outside of the reactor. So there is an internal energy of the surroundings, entropy of the surroundings. You could have a volume of the surroundings, but the volume of the surroundings is the volume of the universe. It's not really useful to talk about the volume of the universe. In order to write it in this particular way, there's something that's equal about both of those two phases. These are the only two assumptions that we really have to make for our quote-unquote real reactor here. And then once we apply these assumptions, we're going to figure out what's the first law say, what's the second law say. These assumptions are, one, temperature and pressure are both constant and uniform. Another way to say this is that they are at thermal and mechanical equilibrium. That is not how you say mechanical. That is. Thermal and mechanical equilibrium. Just another way of saying constant temperature, constant pressure. The next assumption is not an assumption that we have to actually make. It just makes our lives a little bit easier when we do the math. Yeah, okay. That's blue on my screen. I don't know why. The other one is that everything is all one phase. That is not an assumption that is required. You will end up with the same answer that we're about to derive, whether or not things are all one phase or not. Here we're going to assume that everything is gas. Again, that's just to make our lives a little bit easier in terms of math. But you don't have to make that assumption. There's nothing wrong with letting things be multiple phases. In fact, when we get to the final answer that we're going to have in about 10 minutes, it's applicable to systems of multiple phases, which is what makes it so useful. So how do we take everything we learned in 102, everything that we learned in 100, apply it to a system like this that actually exists, right? That's the big difference between anything in 100 and anything here in terms of a reacting system. This one will actually exist, and therefore the second law will apply. We could not have derived this in CENG 100 because we didn't know anything about the second law. So that's going to be our starting point, is the second law. I'm going to give myself a little bit of space over here on the left. And so the stuff on the left is just going to be a brief description of what equation did we use. How did we come up with whatever reaction I started with, or sorry, whatever equation I have. So the first thing that we start with, as I mentioned a moment ago, was the second law. Right? Making no assumptions at all, the second law tells us that, in general, the entropy generation has to be positive. So this came from our second law. Again, that's for any kind of change in the system. So if I take a molecule A and B and I somehow turn it into molecules C and D, that change has to obey the second law. If that change does not obey the second law, in the sense that the entropy generation for the system plus the surroundings went up, that change is not possible. We have, as far as I know, no way to derive the second law. We just postulate the second law. So I don't have a reason for why that is. The universe we live in follows that rule. Any actual change that we put in the system must follow the second law. So anything that actually happens, unless you lock all those molecules in place and don't let them move, don't let them react, any of those changes will follow something like this. So for this one, we have any change. And I'm just going to write right over my name right there. We can get a little bit better from that, make it at least a little bit simpler, if we look at that surroundings term. So this one, if we treat the surroundings as a giant thermal reservoir, which for the most part the universe is a pretty good thermal reservoir, we found an expression in 102 to say the change in entropy is equal to the change, the amount of heat that was added to or removed from the system divided by temperature, the temperature at which that is performed, that change is performed. So we can change this a little bit. Oops, that's a minus sign. By adding something like this. The reason that we can do that is because the change in entropy of the surroundings, or really the change in entropy of a reservoir, and we're counting the surroundings as a reservoir, was defined as dq over T. We had that definition. In fact, originally that definition came from people working on steam engines who realized that this quantity dq over T was conserved going around a loop or something like that. And they said, okay, I'm going to assume that that means there's some conserved quantity like entropy, and all I can do is calculate its changes, which is fine. From a basic energy balance, though, we can relate that to the change in entropy of the system like this. Right? Whichever direction the energy went, if I'm taking my reference as the surroundings, I can figure out the amount of energy that either left or was gained by the system by putting that negative sign in the middle. And so that's what we did, or not negative sign in the middle, negative sign in the front. Any of the energy that went out of the system had to show up in the surroundings and vice versa. So we can relate those two pretty well that way. What we couldn't do, though, was write something similar for the actual system. Because the system is not a thermal reservoir. That's a special definition just for thermal reservoirs. We can't write it for any old system. It has to be a thermal reservoir. So we're still kind of stuck with this ds superscript T form that doesn't really help us too much. So we have to work on that a little bit. So in order to do this, we had used our definition of a reservoir. Now what we can do is use our first law and work on that ds of the total system. Or sorry, work on the dq of the system itself. We can write that in terms of things that are a little bit easier to measure, a little bit easier to quantify. So we'll leave the ds there. We're actually going to leave that there for the entire time. The end result that we're going to have will look like this. I will show you how we got that in a minute. And there's a T out here. That looks pretty different, but we didn't actually do all that much different. And as I recall from last year, people hated it when I did this. But we have technology, and I don't see any reason why I can't do something like that. Oh, I forgot it did that. There we go. I can do that, you can't, but hopefully you left yourself some room there. How did we do something like that? Straightforward application of the first law. What we said was if we rearrange the first law a little bit, we can have something like dq is equal to du minus dw. And the reason that we assumed everything was a gas was just to make this particular step a little bit easier, because we had a nice closed form expression for dw that didn't require a lot of variations on it. That closed form was that dw is equal to minus p dv. That just makes our life a little bit easier. We don't have to make that assumption. That's why assumption number 2 on a couple of slides ago was sort of optional. It makes our life a heck of a lot easier in terms of this derivation, but it's not required. If you take those two expressions, the first law on the top and then this definition that we have underneath, put them back into the expression that we had up top, do a little bit of math, rearranging that sort of stuff, you will end up with what we see in that line. We move the t around a little bit. You're never going to have to derive this ever in your life unless you have a thermo book in front of you. Don't worry if you can't follow that right now. You can prove it for yourself when I assume that you go home and study thermodynamics all night. Another professor and I have both been on this really tiny sort of obscure esoteric aspect of exactly this, and that is what I do. It's quite enjoyable, actually. It's like 9 o'clock or something, and we're thinking about thermo. It's actually a lot of fun. Try it. Try it. Nobody's going to try it. How do we go one step further? One step further, we have to use two definitions that we came up with we kind of introduced one of them, enthalpy, in 100. Remember, we just arbitrarily defined enthalpy as U minus PV. And we said, why do we do that? Because those two things come up all the time. Sorry, U plus PV. We do it because it's convenient. There's no reason other than that we have to do something like that. So if we use something like enthalpy, we can change this a little bit more. We start off with the same ones here. We still have P dV total. And now we can replace, instead of talking about internal energy is not particularly useful when it comes to actually measuring something, swap it out with enthalpy. If you swap it out with enthalpy, you end up with something like dHT plus P dVT. Has to be greater than or equal to 0. The reason that we can get away with that, actually, I'll just write this over here, is because you can write that the change in enthalpy is equal to the change in internal energy plus P dV at constant P. So you can kind of see our original definition of enthalpy over there. Enthalpy is equal to internal energy plus P times V. That's just that in its differential form at constant pressure. There's nothing particularly new there. It kind of looks like we made things worse, but some of that looks okay, right? There's at least a step in the right direction because we have a minus P dVT here and a plus over here. That's nice. So those two will cancel out. We need to make one more. I wouldn't even call it, it's not an assumption, we're using another definition. Who remembers the fun of Gibbs free energy in 102? You would have gotten the G term in 102. It's coming back, and we're going to use it a lot. It comes up all the time. But Gibbs free energy, just like enthalpy, was completely arbitrary. It's a useful thing to define. It is expressing something that we can calculate in terms of measurable quantities, namely temperature and pressure. That's why Gibbs free energy pops up so often, is because it's got temperature and pressure in it. We have a ton of probes that'll measure pressure and a ton of probes that'll measure temperature. That's why we use it so much. So if we do that, I'm going to have to switch over to another page over here. We can simplify this down one more step to TdS minus dHT. This will be equal to minus the change in Gibbs free energy for the system, and all of that has to be greater than or equal to 0. The reason that we can get away doing something like that is very similar to the last step, which is that the change in Gibbs free energy is simply defined as dH minus TdS. And again, that's at constant temperature. The full form of that is the change in enthalpy dH minus the change in entropy times temperature, but if temperature is constant, you can pull it outside the derivative, which is what we did here. And so that is our jewel, our gem. Everything that we have been going for was this. For any real system, if something happens in that system, if anything happens, sorry, I drew that the wrong way, anything at all, we don't care what kind of change that happens to be, if that change is real, if it actually happens in our system, then the change in Gibbs free energy will be less than 0. Which means if those two things react at all, the result is that dGT, the Gibbs free energy of the system, went down. If it didn't go down, it wasn't a real change and it wasn't a real system. That is why this thing gets all the boxes. I mean, like a ton of boxes. Take a look at a thermo book. You are going to see that particular expression an awful lot. This is big in chemical engineering. Why is it so big? Sorry, I had, there was one more note. Little tongue and an eyeball in there. It's huge. The reason that this is so big is because it's the first time we can really say what happens in a real system. And the other reason it's so important is it's so broadly applicable to any kind of change that you might experience. Remember, I had briefly said when we were writing those assumptions, it doesn't have to be for a single phase. So if you think of things that require phase changes, they all obey that particular rule. If it's real, then the Gibbs change was less than or equal to 0, if anything changed. So if you're talking about, why does an oil and a water separate, something like that, even if I sit with a bottle of oil and water, which I tried to get one of these, but apparently there's no oil on this entire campus. If I shake that up, why do they end up separating? Part of the reason for that, it's kind of at this point we can't quantify that, is because of this particular expression. Anytime you have a phase change, whatever happens after that is going to be dictated by this particular expression. That's in addition to any of the reactions that we might have, and reacting systems are pretty big. There's a lot of those. You can also mix the two. If it's a multi-phase system and reactions are going on, they still obey this particular expression. Yes?
Does this also apply if we force a change to happen? Because if it was less than 0, it would be spontaneous, but if it wasn't spontaneous, then you would have to force it.
Yes, so when you say you force a reaction, what you have done is rejigger the system so that that's true. Right? You've heated it up or something like that so that your expression for the Gibbs free energy represents that. Yes. That's what we mean when we say, well, reactors typically have to be hot. Why do they have to be hot? Because then this is going in a direction that we want. You can actually plot something like this, and you will plot something like this on your first homework. And so what those plots tend to look like, let me see if I can change the color of this real quick. Right? If you are lucky enough that you can actually plot this in 2 dimensions, you can try to get away with it in 3 dimensions. More often it's multi-dimensional and we can't plot it at all. But you're going to plot a 2-dimensional version. And this curve might look something like this, where over here on the y-axis is the Gibbs free energy of the system. Remember, these are always at constant temperature and pressure. So in 102, we said whenever we need to denote something at constant temperature and pressure, we put it in parentheses and put a subscript TP on there. If you are in a reacting system, your x-coordinate might be something like squiggle. Wherever you are on that system, right, wherever squiggle happens to be before you start the reactor, let's say the squiggle is up here. You have 2 choices for that system, or that system has 2 choices. It doesn't actually get to make the choice, it just happens. You can either move up that curve or you can move down that curve. What that curve means and what that rule is that we just derived is that if I start here, the only option is for that system to move down the curve. Right? So the squiggle, the extent of reaction, will move to the left. Same thing happens if I'm on the other side. If I started off over here, my only option is to move in that particular direction because the Gibbs energy is going down. It reaches a point where it doesn't move anymore. Right? Eventually, it hits this point down here. Right? I can't move to the left or the right because if I move to the left, the Gibbs energy will go up. If I move to the right, the Gibbs energy will go up. Those changes simply will not happen. Actually, that's a good question that was just brought up a minute ago. How do I shift it off of that point? I got to change the system somehow. Right? I got to change the temperature so that that curve changes and now it starts falling down a different curve. But if you don't change the temperature or the pressure, you are stuck at that minimum point. And that's 2 of the big requirements for any kind of chemical reaction. It's not necessarily a chemical reaction. One of them is that if this is a real system and it's not changing anymore, or you have let the reaction run as long as it can, then GT is minimized. So if you ever hear somebody say, and you will hear them say it as you go through chemical engineering, the Gibbs free energy is a minimum, this is what they're talking about. You have reached this point in the curve where any step in any direction, if I change something, if I react a little bit this way and a little bit that way, it's not going to happen. It just won't happen. The second law says that change will not happen. Yes? Yep. It's an internal property of the system. It's kind of like internal energy, where we're talking about the energy that's available for some kind of a change, except it's Gibbs free energy. There's a special name for this reactor. It's called a Gibbs reactor. A Gibbs reactor is an idealized reactor. It only occurs on paper. You never actually have a Gibbs reactor. But if you're in a situation where you have no idea about any of the reactions that are actually happening, you can always pull off a Gibbs reactor and figure out what's possible. You're going to do one of those in the homework. That's one criteria for this point where the system stops changing, is that GT is minimized. From calculus, though, there should be another indicator of what's happening at that particular point. The other requirement for that point is that the change in Gibbs free energy with respect to something, in this case we're going to call it squiggle, at constant temperature and pressure is exactly equal to 0. Right? That's what that points mean. Calculus means if you're at the minimum of a curve. There's actually another one where you can be at a maximum. It's not a stable point, so it tends not to be referenced very often. But if the system is at this low point in the curve, then we know the partial differential of GT with respect to squiggle at constant T and P has to be equal to 0. This is the one that we'll spend most of our time in class working on because it gives us an equality. We can actually solve that equation for something. The first step up here, though, is, in practice, the one that gets used more often. The reason being that the one on the bottom is only good for a single reaction. You can't write a very neat-looking expression, for any kind of multi-reaction system for something like that. I think I might have blurted it out. Anybody know what the name of that dot is? So the system is at equilibrium. That's why this is so important. It says thermodynamically, this is where the system will be at equilibrium. That's what that little green dot means. The key thing in the wall that we hit in 100 and 102, if we do something like this, is it doesn't tell you how long it takes to get there. There's no element of time here. That's a fundamental limitation of the tools that we have right now from 100 and 102. We can't talk about time. It could take 1 second to go from the yellow to the green, or it could take 40 years to go from the yellow to the green. All this is saying is if you give it long enough to hit equilibrium, where's it headed? That is, however, extremely useful because it sets a cap on what's thermodynamically possible. And that's a pretty useful thing, right? If I don't know anything else about a system other than what's the best I can do, I can go a pretty long way in terms of evaluating whether or not that system is profitable. Right? The best case scenario is to get to equilibrium. It might take me 40 years, in which case I would throw the system out because it doesn't work any well. But at the very least, equilibrium will tell me where I'm headed. And that's one of the reasons that we use it so much. It establishes a sort of like an upper bound. What's the biggest change that we can get? Well, whatever change ends up taking you to equilibrium. That comes up, I'm just going to go back a page. The reason that this comes up so much, like I said before, is because it works for phase changes, it works for chemical reactions, it works for mass transfer. So all the common pieces of equipment that occur in chemical engineering that you'll pick up either in like 102, it doesn't really work in 101A, 101C, 120, 122, 176, 124. Things like distillation columns, I have a list here, crystallizers, mixers, reactors, flash columns, distillation columns, all that stuff, every one of those pieces are talking about equilibrium, which all follow this particular expression. The nice thing about that expression is it's not just equipment that you'll encounter in chemical engineering. It shows up other places. For example, a lot of the stuff that you get out of your house will have something to do with equilibrium. If equilibrium is achieved somewhere, if particles move from one place to another by anything other than actually flow, like moving them, they are subject to these constraints. So like coffee makers have minimization of Gibbs free energy. I have another list of these. Some of these are pretty good. Any kind of colloidal suspension that you have, so how come milk stays separated for a while and then eventually, how come milk stays homogeneous for a while and then separates? It is slowly reaching its thermodynamic equilibrium, which can also be changing due to a reaction that's occurring. Your toothpaste is a good one. There's a lot of different particles that are in suspension in there. I'm just going to list all of these because I had a lot of fun sitting. Again, this is what faculty do. We sit there and think of examples of equations. Okay, so I have 2 minutes. Coffee pots, tea kettles, refrigerators, chocolate, moisturizers, Tylenol, cold and flu, cellular processes like in your body, central air, water filters, toothpaste, shaving cream, Advil gel caps, car engines, car batteries, central heating, water softeners, mouthwash, salad dressing, digestive systems, motor oil, beer, wine, any kind of spirit that you have. Anything that you've got that has more than one component in it is probably subject to this particular equation. Because that particular equation is saying, what's that thing look like if I just let it sit there for a really long time? That's a pretty useful piece of information. We're going to study that equation for about the next 3 days until we can't study it anymore, and that's when we actually start the stuff in 113, which talks about time. So I will see you all Wednesday. Keep your eye on your email, too.